All right, class, today we're going to be talking about exponential growth. So let's get that down. So we've got, be talking about exponential growth. What are some things that grow exponentially? Well, I mean, what exponential growth is it is a rate of growth that is based on the amount of things that are already present. So, for example, I'd say the most common example is just an investment, right? So, if you invest a lot of money, your return should be a decent amount of money. If you invest only a tiny bit of money, your return is only going to be a tiny amount. So your return is just based on the amount of money you put in. That's generally how that's generally kind of the hope of how investments work. Other things is like population. So like a bacteria. If you are growing a bacteria, let's say in a petri dish or something like that, and you only have maybe one or two specimens in the petri dish at a time, the first few days, yes, it'll grow, but it'll grow pretty slowly. However, if you have a lot of it there, and they all, sort of split and reproduce themselves, that means, well, now you actually have a great many of bacteria. And so if you have a lot of bacteria, so basically population growth in a very basic form is also exponential. So that's kind of the exponential growth thing. There's also exponential decay. And decay is sort of like, a good example of decay is the value of something. So like a car's value, if you go and buy a car for $30,000, when you drive it off the lot, it drops significantly. It drops, in that first year, it drops from 30,000, down to 20,000 in the first year. But then if you own a $2,000 car, kind of a junker or something, if you own a $2,000 car, the next year, it's still basically going to be worth $2,000, like maybe a little bit less, but it's not going to lose that much value anymore because it's not worth that much. So that would be kind of an example of exponential decay. So that's what we're going to be working with. All right, so let's go over the formulas. So exponential growth and decay. The formula is the final is going to equal the initial times the rate to the power of time. Okay? Now, this is just sort of the basic idea. So if I said, this would be sort of the idea of the bacteria, right? So let's actually do one like that. So if I said, you start with, let's say 7 bacteria, which triple every day. How many do you have in a week? Well, if you start with 7, that means your initial is 7. If it triples, that means your rate is 3. So if it doubles, your rate would be 2. If, whatever the multiplication is, that's it. Or if it if it decreases by 1/2, your rate would be 1/2, or, something like that. So, so when it says, so if it's just a general rate of increase, that's just R. So every day, how many will you have in a week? So what we're asking, well, what is the final if the initial is 7, the rate is 3, and in a week, since we're saying it triples every day, when we say a week, the T must be in days, because we did this rate is happening per day, so how many days in a week? It's 7. So we have this formula right here. And let's see here. I need to get my. Okay. So 7 times 3 to the power of 7. This is going to be about 15,309 bacteria in our petri dish at the end. So that's sort of an example of just a general rate. We can also ask, like, we can ask how long till we have, let's say, 100,000 bacteria. Well, if I'm asking for a time now, we're saying the final equals, till we have that. That means that is the final. So 100,000 equals the initial 7 times the tripling, but we don't know the time now. So to do this, we need to use, we're solving for an exponent. So since we're solving for an exponent, we need to use a log. So to use a log, we divide by 7. So again, we're going to have 5 divided by 7. So here we go. So when I divide this thing by 7, I get 14,285.7 equals 3 to the power of t, which basically means log base 3 of 14285 equals t. So we have to use a logarithm here. Now, if you have a calculator like this, you can use your log base, right? Log base, where I put 3 in the bottom and 14,285 up here, in which case I get basically how long? Well, that's really easy. Yeah, this is basically saying 9 days, right? So it says 8.7, so we'll just round it to the nearest day. So this is 9 days. So that's how you use a log. Also, by the way, if you don't have a calculator like this, you would do log of 14,285 divided by log of 3 by using the change of base formula. Log of 14,285 divided by log of 3. So just to get a good look at that, hitting enter, notice we get the same answer. So that's kind of like general. But what about a percentage? Okay, so that's just a general thing. So now what if you have a problem with a percentage? So let's say you have the stock market is usually projected to increase at about 7% each year. Assuming this and an initial investment of $5,000, how much money would you have after 7 years? So again, 7%. Now, if it's a percent, so if percent growth, then your formula is F equals I. Now, you need 1 plus the rate to the power of time. If it's decay, if it's a percent decay, you need F equals I 1 minus R to the power of t. Sorry, I didn't realize I was off the screen. So if it's a percent growth, you need this. If it's a percent decay, you need this. The only difference is plus and minus. This is clearly you're trying to make money. So you're trying to increase, so it's a percent growth. So here it is. So this is the final equals your initial investment times the rate. Now, in this case, the rate is 1 plus 0.07 for 7%, right? So 1 plus 0.07 to the power of t. In this case, t is 7 years. So we're going to put a 7 up here. There we go. So this is just a very heavy calculator problem. 1.07, I'm just adding those two right away to the power of 7. Now, this means that after 7 years, we will have only $8,029 if I was rounding to the nearest dollar. $8,029, right? Rounding to the nearest dollar. So, there you go. How long would it take to go to 50 years? So it took 7 years to go from 5,000 to 8,000. That seems like a very long time just to go up about $3,000. So to get to 50, it must be a really long time, right? Well, let's see. So we're going to say 50,000 equals 5,000 times 1 plus 0.07 to the power of time. So we're going to divide by 5,000. So by the way, 50,000 divided by 5,000 is actually just 10. So 10 equals 1.07 to the power of t. To solve this, we change this into a log. Log base 1.07 of 10 equals t. And so, calculator, I'm going to use my change of base function here, 1.07 to the power of 10 equals 34 years. So it actually doesn't take that long. Once it gets going, and that's what exponential growth does, right? At first, it's growing pretty slowly here. Notice to only get to only go up $3,000, it takes us 7 years. But to go from 8 to 50,000, it just takes us, to go from 5 to 50, it just takes us 34. So very slow at first, but must be picking up quite a bit. So it's only 34 years now. So that's kind of exponential growth. Let's do an exponential decay model. So let's say you buy a car. Okay. You buy a $30,000 car, which depreciates at 15% a year. Okay, so let's first write the model. So model this. Oops, man. So this is $30,000 times the rate, which, since it's a depreciation, we're going to use the minus to the power of t, right? So that's the model. Now, what about how much is it worth? In 3 years. Well, that's pretty easy. That's final equals 30,000, 1 minus 0.15 to the power of t, which in this case is 3. What we're asking here is 30,000 times 0.85. Now, this should make sense because basically what you're doing is you're saying, all right, after every year, how much is this car worth? Well, after every single year, the car is worth only 85% of what it used to be. And so that's why it kind of makes sense to do the subtraction, right? It's not worth, while if we had put a plus here, it would have been 115% of what it used to be, right? But we want this to decrease, so that's why we're saying minus. It needs to be worth only 85% of what it used to be. So that's kind of the idea of this 1 minus and this 1 plus. But in any case, let's plug this in. So we've got it is worth $18,423 or $4. We'll go with 4 rounding. Okay. How long? Yeah. How long till it's worth only $5,000? Well, that means 30,000. That means 5,000 is your final, equals 30,000 times 0.85 to the power of t, and we need to solve for t. So we're going to do 5,000 divided by 30,000, right? And that's basically, the thousands are going to cancel, and so you're going to get 5 over 30 equals 0.85 to the power of t, like so. In other words, log base 0.85 of, this by the way, is just actually 1/6 of 1/6 equals t. So, plugging that in, math, 0.85, 1 divided by 6, we get 11 years. And so that's basically how you solve these exponential problems. So why don't you take a look at your homework? I think they're fairly straightforward. You can always shoot me a remind message if something's confusing. Thanks.